innovation, inspiration, fusion. CHASSpark website, together with you, driving global scientific and technological progress. Where does progress in science and technology come from? From insights gained through practices, from sparks of discovery, from inspiration sparked by the clash of ideas, from elevation achieved through the fusion of different perspectives. In 1654, Pascal and Fermat opened the door to probability theory in their discussion on the problem of points. In 1687, Halley persuaded the hesitant Newton to write his great work, Mathematical Principles of Natural Philosophy. In 1736, Euler attempted to solve the puzzle of the 7 bridges of Königsberg, which led to the creation of graph theory. In the early 20th century, Einstein and Bohr collaborated and completed to develop the theories of general relativity and quantum mechanics,
两位老师好，
respectively.
我看到都上线了。
In 1936, Turing began to explore the universal Turing machine while studying computable numbers. In 1945, von Neumann, who joined the Manhattan Project, introduced the 3 laws to the computer field. In 1948, Shannon proposed information entropy and Shannon's theorem after discussion with von Neumann. In the early 20th century, Fields proved the Riemann-Roch theorem and dedicated himself to global mathematical communication. In 1941, Hedy Lamarr and George Antheil invented a frequency modulation technology, which was implemented in wireless communication systems. In 1965, Gordon Moore summarized practical experience and proposed Moore's Law, which has since been widely followed. In 2000, Gao Kun spearheaded the development of the world's first 1-kilometer-long optical fiber network. In 1986, Geoffrey Hinton applied backpropagation to deep learning. Scientific research and technological advancement progress incrementally in this way. Link up theory with practice and aggregate resources. Make active exploration and innovation. Discuss and exchange ideas to ignite inspiration. Develop talent and the ecosystem. CHASSpark website. Aggregating global high-value scientific and academic information. Offering multiple intelligent and efficient services. Connecting global academic, technical, and talent resources. Connectivity, innovation, inspiration, fusion. CHASSpark website, together with you, driving global scientific and technological progress. Where does progress in science and technology come from? From insights gained through practices, from sparks of discovery, from inspiration sparked by the clash of ideas.
Welcome to the mini-course series, Fundamentals of Channel Knowledge Map, from classic to AI-based math. Here comes to our lecture 4.1, Dataset and Prototyping for Intelligent CKM, delivered by Professor Yong Zeng. It's my honor to introduce Professor Yong Zeng, an Attribute Fellow and Full Professor at National Mobile Communications Research Laboratory, Southeast University of China. Professor Zeng received a PhD and bachelor degrees, both from Nanyang Technological University, Singapore, in 2014 and 2009, respectively. Professor Zeng serves as an editor for IEEE transactions on communications, IEEE transactions on mobile computing, and IEEE communications vectors. He also takes conference leadership as workshop co-chair for various workshops in related areas. Professor Zeng also received numerous honors and recognitions, including Web of Science, highly cited researcher in the recent 7 consecutive years, ImageNet Prize Paper Award in Wireless Communications, both in 2020 and 2024. IEEE Communication Society Acer Pacific Outstanding Young Research Award in 2018, IEEE Communication Society Heinrich Hertz Prize Paper Award, both in 2020 and 2017. Professor Zeng got a Google Scholar citation for more than 37,000 citations, and Professor Zeng is also a proposer for the CKM concept. So without further ado, please join me in welcoming Professor Zeng.
Okay, yeah. Thanks, Professor Chen, for the kind introduction. Let me share my screen first. Okay, yeah, I believe that you can see my screen now.
Yes, we can see a screen.
Okay, yeah. Hello, everyone. Thanks again for joining us today. Today, I'm going to share with you some data set and the prototyping systems for channel knowledge map. So here is the outline. I will first discuss why we need a dedicated data set for CKM, and then I will introduce one particular data set called CKMImageNet, and we will also introduce a platform called CKMImageNet, which is a platform to generate CKM very efficiently. And then I will introduce some preliminary prototypes for CKM. So let me first recap our definition for channel knowledge map. So we consider a wireless system. It can be a wireless communication, localization, sensing, or navigation systems. So we have a transmitter at location QT and a receiver at location QR. In order to reflect the actual wireless environment, we can actually define the transmitter and receiver location vector Q that includes both QT and QR. And then CKM is defined as a mapping from this transmitter receiver locations Q to channel knowledge vector Z. So if you give me the location vectors Q, QT, and QR, then CKM may give you some prior knowledge about the wireless channel Z. So you may wonder what should be the channel knowledge Z based on our previous definitions. Any information that is useful to reduce the channel uncertainty can be our channel knowledge. So we do not use the terminology channel map or radio map because we want to have a very generic concept. So it can be the angle of arrival, angle of departure, delay, or the conventional channel strength or channel gain. So a very fundamental problem is how to construct the CKM or channel knowledge map. So this is the basic setup for CKM construction. Let's say we have some data set. So this data set can be from the historical measurement, or it can be from the some dedicated simulations. So we will discuss the sources of the data set later on. So the key point is that the data set will include the location-specific channel knowledge. So let's say at the nth point, QM, we have the corresponding channel knowledge, Zm. It can be the channel strength, it can be the angle of arrival, delay, and so on and so forth. So with this data set, we want to construct a channel knowledge map for certain environment, let's say Q2. So by the way, the data set may be connected from another environment, Q1, another area, Q1. But we need to specify some environmental information about the environment where we need to construct the data, the CKM. So here we may have some environmental knowledge epsilon, which specifies the actual environment we need to construct the channel knowledge map. Fundamentally, we need to find all the possible locations Q, what is the corresponding so-called location conditional channel knowledge. So we have two possibilities. The first possibility, as we mentioned before, is that the data set we collect, the area to connect the data set is Q1. It is the same area, Q2, where we need to construct the CKM. So this is a rather simple problem for CKM construction. The more challenging one is that if our data set is connected from another area, Q1, but we want to construct a channel knowledge map, CKM, in area Q2. So Q1 may not be the same as Q2. So this basically requires us to transfer the knowledge learned from the data set from one place to another place. This is more challenging. So if we consider the CKM construction problem, actually we have three possibilities. Depends on how much knowledge or how much information we have for the environment where we need to construct the channel knowledge map. The first case is that we do not have any environmental specification for the area where we need to construct the CKM, but we only have some data. So this is the first case. The second case is that let's say we want to have the CKM for area Q2, and we have the full environmental information, including all the, let's say, the building locations, building height, and also the materials of the environment. So this is actually much simpler because we can use, let's say, we can use ray tracing to find the CKM. But the third case is that let's say we have some partial environmental specification, and simultaneously we have some data set or data from some data set. So this basically means that we can learn the information from two sources. The first source is that we can learn the information from the environment specification. The second source is that we can learn the feature from the data in the data set. So this will actually give us a more practical scenario for CKM construction. So here in this talk, we will consider the third case, which is the most practical, most challenging case. So, but if we consider the so-called non-transferable CKM construction, it basically means that if we already have a large data in the environment where we need to construct the CKM, basically we can use some interpolation methods. Let's say IDW, nearest neighbor, KNN, or Kriging method, or even we can train a deep neural network to map from the location information to the channel knowledge. But this is the first scenario where the data we connect the data. The area where we connect the data should be the same area where we need to construct the CKM. But for the second case, for the transferable CKM construction, we found that it is quite similar to the image processing problem as we discussed previously. So the basic idea is like this. So let's say if we want to reconstruct this image, let's say the image for a dog, but we only have the partial observation of this image. So this is very similar to the scenario where we need to construct a CKM for area Q2, but we only have some partial observation for this area, but we do not have the complete environmental information or complete observation. So in this case, in order to construct the CKM or in order to reconstruct this image, actually it is a so-called ear-posed problem, because there are many possibilities where this partial observation may correspond to. But fortunately, if we have another source of information, which is information from the data set, we may learn the patterns or some probability distribution of these images so that it will help us to reconstruct this restored this missing image X hat. So this is actually fundamentally different from the conventional interpolation-based methods, let's say the KNN or nearest neighbor method, because for that method, they do not learn from the large data set. So for our problem, it's quite similar. Let's say we only have partial observation for the environment Q2, where we need to construct the CKM. So if without any additional source of information, it is quite difficult to reconstruct the CKM perfectly or with low error. But if we have some data set, then we may learn from this data set. For example, the feed pattern of a CKM should look like this. So in this case, we can learn some prior distribution of CKM for all the data collected in all areas. It is regardless whether it is collected from the Q2, where we need to construct the CKM, or it is collected from any other places. So this is a fundamental problem for so-called transferable CKM construction, where we need to learn from both the data set and also we need to make use of the environmental specifications for this environment where we need to construct the CKM. So in this case, the data or the data set is very, very important. So actually, data set is vital to any AI models. There is a philosophy called for any AI models, if we have garbage in, then we will have garbage out. So how to assess whether a data set is good or not? So there are different aspects. For example, in terms of the quality and the quantity, so it should be accurate enough. So for example, for our CKM data set, we need to reflect the actual wireless propagation environment and also to obey the wireless propagation laws, let's say the phase transmission equation or some other physical laws for wireless signal propagation. And it should be at least spatially consistent. For example, if one data point indicates that there should be a wall in this place, but another data point indicates that there's enough site, there's no blockage, there's no wall, then this data set is not spatially consistent. So for example, for our traditional stochastic model, let's say the relay or region feeding model generated data, it cannot ensure spatial consistent. So that data cannot be used or will be poor quality for our data set for CKM construction. So another requirement is so-called completeness. For CKM or channel knowledge map, we expect that the data set should contain enough channel knowledge. For example, not just for the channel gain, but also the signal direction, the delay, and so on and so forth. And then we should have high diversity, and we should have a large data set in order to avoid overfitting. So these are the basic requirements for CKM data set. And of course, we have some other requirements. Let's say in terms of the format and the structure, the data should be well organized in standard format. For example, if we have a text, image, or table, then we should format those data in the standard manner so that any AI algorithms can process the data very efficiently. And if we want to use supervised learning method to train AI model for CKM construction, then we need to ensure that the data should have a clear annotation or labeling, and so on and so forth. Of course, we have some legal issues and privacy issues for dataset. So in terms of the CKM channel knowledge data acquisition, actually we have different methods. For example, the data can be connected offline by simulation, by actual measurement, or it can be collected online for real-time measurement. For example, whenever a mobile phone is communicating with the base station, actually the link will estimate the channel. It actually generates a lot of channel knowledge. So this kind of data can be connected and stored online so that we can learn the channel knowledge map. So in terms of the data sources, there are also different possibilities. For example, the data could be generated from some models. It could be from some ray tracing simulations, from some historical data, or some dedicated measurement data. So the first question we want to ask is, if we want to build a useful data set for CKM, which method should we use? Should we use the model-based method, measurement method, or synthetic-based method? Actually, in the AI community, there's a concept called data pyramid. We have the similar concept or similar scenario here. The first method we can think of is the channel model-based data. Because during the past few decades, the wireless community has established quite significant channel models. For example, we have the relay fading channel model, region fading channel model, and for 3GPP, we have different channel models. And based on these channel models, we can easily generate the channel knowledge or channel data. And it is actually very easy to generate. But the key limitation for this kind of data is that it has a very weak coupling with the wireless environment. For most channel modeling, it does not even consider the specific environment. So the key limitation is that such kind of data has low fidelity because it cannot reflect the actual wireless environment. So maybe this kind of data is not very useful, because if you use this kind of data to train an AI model, what you can learn is just the channel model itself, the stochastic channel model itself. Let's say you will end up with a relay fading channel modeling or region fading channel modeling instead of the location specific channel knowledge map. So another possibility is the synthetic data. Let's say we can use the ray tracing, let's say the wireless insight or Siona software to generate the channel knowledge data. The key advantage for this kind of method is that we have the full control for the environment, and it is easy to generate. And the data is environmental consistent or spatially consistent, because the ray tracing will consider the actual wireless environment, whether there's a blockage, whether there's a reflection, diffraction. So this kind of propagation mechanisms will be considered by this kind of ray tracing software. And we can easily generate a large quantity of data. But of course, in order to have a very realistic data, we need to have a measurement data. Let's say we need to conduct the dedicated channel measurement. But the key limitation is that measurement is usually high cost and the data is very scarce. So actually, during the past few years, there are quite significant research efforts trying to use the second approach, which is the synthetic data, to generate some data set. So we will briefly introduce a different data set. The first dataset we will try to introduce is called radio map seer. So this is a dataset that mainly gives us the channel gain or the path loss. And it assumes that all the buildings have the same height when they do the ray tracing scenarios. So this is a big limitation. So another data set is a deep MIMO data set. So similarly, it uses ray tracing to generate the MIMO wireless channel data. But the key limitation is that it does not consider the location specific or the location tag is missing. And we have the deep sense 6G. In this case, they have the GPS location information, and this kind of data set is constructed not by the simulation. It is based on the real-world measurement, but the data size is rather limited. And we have the M-Cube SC dataset developed by Professor Chen Xiang's group in Peking University. So we have the different data types. Let's say the RGB image, depth map, point clouds, and the key scenario is in the vehicular communication networks. So in this case, they consider both the sub-6G and the millimeter wave, and they use the simulation methods to get the different different data models. And then they further extend the data set to the to this scenario to consider also the data point clouds. This is called SENS SOM data set. So they use the simulation with the same software as the M-Cube SC, and they also validate some data by the real-world measurements. So this is a very useful data set. But in terms of the CKM construction, such existing data sets actually are not sufficient, because for CKM construction, we need the location-specific data. So the channel knowledge data itself should be tagged by the location information. So many of the data sets do not have this kind of information. And we not only need to have the signal power or channel gain information, we also need to have the angle or propagation delay information. And we try to visualize the data set because we try to use the computer vision techniques or CV techniques to support the CKM construction and the utilization. So how to visualize the data set is also quite essential. So most of the data set in the existing community, wireless community, do not have this kind of visualization effect. And of course, we need to have the tight environmental specific data set, and most of the data set will meet this requirement. So in order to meet all the requirements, we need to propose a dedicated data set for AI-based construction and utilization for the purpose of channel knowledge map, because the existing data sets were designed not for the specific purpose of CKM construction. So we need this new data set called CKMImageNet. So what is CKMImageNet? If you are familiar with some AI algorithms, you may have heard this of data set called ImageNet. So actually, this CKMImageNet is inspired from the computer vision community. They have the data set called ImageNet, which was developed around 2009. And it was originally designed for the object recognition or classification research. It contains over 14 million annotated or labeled images and with 20,000 categories. So it has been widely used for computer vision, especially for the image classification and object detection tasks. And why this ImageNet is so important, because it is widely recognized or widely regarded that the success of ImageNet, which is a data set developed in 2009, together with the model called AnnexNet, which uses the CNN deep convolutional neural network to perform the object recognition tasks. So ImageNet plus NXNet, of course, together with the advancement of the computing resources, let's say the GPU, will actually marks the starting point of the modern AI era. So that's why ImageNet is very important for the AI community, and it is a large-scale data set. So motivated by this kind of data set, we try to propose or develop our data set for CKM or channel knowledge map. So what is CKMImageNet? CKMImageNet is a large-scale data set trying to give the channel knowledge data reflecting the actual wireless propagation environment and also the wireless propagation laws. It contains the rich channel knowledge types, not just for the channel strength or the path loss, but also the multipath AOA, AOD, and delay. These are very important for tasks, let's say the wireless sensing and wireless localization. And we discussed this how to use CKM to enable wireless localization and sensing maybe 2 weeks ago. And we use the ray tracing technique to obtain such a data set. We use wireless insight and also Siona. So the key idea is like this. We need to consider a very specific environment. We should to specify the locations and the heights and the materials of the environment. And then we use ray tracing software to generate channel knowledge data that is consistent with the actual environment. And then we further do the visualization task so that we can convert all the channel knowledge into images. So that's why we name this data set as the CKMImageNet, because all the data in the data set can be accessed like an image, so that we can use the computer vision techniques to process the data. So the basic procedures for CKMImageNet is like this. We need to first select a region. For example, we select a region in Beijing City, and then we consider this area, and then we use a Blender modeling so that we can generate some environment model to be input to this simulation tools. This is the wireless insight and the Siona. Of course, we also need to specify the base station and the UE deployment and the parameters for the channel knowledge data. Let's say the frequency, the height of the transmitter, and the height of the receiver, and so on and so forth. And then we will net the simulation software to process these ray tracing tasks so that we have the numerical data. Let's say we have the numerical data for the channel gain, for how many paths we have, for the channel strength, angle of arrival, angle of departure, and the delay of each path. And then this numerical data is not very efficient to process, so we also perform the image visualization processing so that we have the image data set to reflect the channel gain map, angle of arrival, angle of departure, and the delay, and so on and so forth. So these are the basic procedures for how the data in CKMImageNet was generated. So the details can be found in this TCOM paper. So we consider the following image visualization. So for each ray tracing task, we consider an area of 400 meters by 400 meters. And the base station is at the center. And we divide the area into grades of 2 meters each. So this basically means that for each ray tracing task, we will result data for 200 by 200. So basically, we will have all the channel knowledge for the 40,000 locations or pixels. But we do not store the data by this kind of 200 by 200 pixels. We actually further divide the region into 49 overlapping subregions. So so that we will have the data or the image size with 128 by 128 pixels. So each image in our CKMImageNet dataset will have the pixel of 128 by 128. And we also have another possibility, another kind of category called use 64 by 64, so that in case you do not have the sufficient computation capability, then you can use the low resolution dataset with 64 by 64 pixels. So the key characteristics of CKMImageNet is like this. It includes multi-band. It covers 3.5 gigahertz, 6.7, and 28 gigahertz frequency band. It considers the 3D actual environment, so we specify the building locations and the building heights, and also the materials. We consider the full-dimensional channel knowledge, not just the conventional radio map or the channel gain knowledge, but also the signal directions and the delays. We consider the multimodal data fusion. We consider the physical maps, base station information, channel data, and visual images. And all the data are organized as image for ease of computer vision algorithms. We also consider the 3D CKM for the low altitude airspace. So we have 3D CKMs for different heights. And currently, this data set has about 500,000 of the image samples. So it is sufficient to train some moderate size of the AI models. So here is how it looks like. So we consider the 3D actual environment. Let's say we specify the building locations and the building height, as well as the materials of the building. And this will be the input to the ray tracing software. And this is how data in the CKMImageNet dataset looks like. We have the physical map of the data, of the environment. And then we have the corresponding, let's say, the channel gain map. So as we mentioned just now, for each image, we have the 128 by 128 pixels. So this basically means that over 10,000 locations or pixels for each image. And we also have the angle of arrival, angle of departure. So we have the multimodal data fusion. So we can have the physical maps and the base station information and the visual image. Of course, if you do not want to use the computer vision techniques to process the CKM ImageNet dataset, we also have the original numerical data. You can use the numerical data to train or to process whatever algorithms you want to use. And for the 3D CKMs, we consider the different altitudes or different heights. So here, let's say this is the same physical environment. And then we have the corresponding channel gain map on the ground. And for height at 20 meters, 40 meters, and all the way to the 100, I think it should be 120 meters. So in this case, you can train a neural network, AI models, based on these 3D CKM datasets. And here is how the data samples in the CKMImageNet looks like. So we have the different base station locations, the different environment, and we make the dataset publicly available on GitHub. You may have a look, and you may freely use this dataset. So here, let's say we have the Beijing, Boston, or college, or LA, all the different cities. And then we have the angle of arrival, both the elevation angle of arrival as well as the horizontal angle of arrival. So we have the full dimensional data in the CKMImageNet dataset. And we also have, as we mentioned just now, we also have the original dataset, numerical data in the dataset. Let's say we have the coordinate and we have the channel knowledge, corresponding channel knowledge. Okay. So let's say if we already have this kind of data set, how can we make use of the data set to train an AI model or to perform a CKM construction? So we have the different possibilities. Let's say we may use the data in the CKMImageNet dataset to perform the CKM generation task. Let's say our input is just the physical environment map plus the transmitter locations. Without performing the ray tracing software, can you train an AI model to learn the data features or the data patterns in this CKMImageNet dataset so that you can generate a CKM that is consistent with this physical environment map? So this is the CKM generation problem, and we need to make use of the data set. And the second case is the so-called CKM implanting or super resolution. The scenario is like this. Let's say if we can measure the channel knowledge in certain locations, but not all the locations. Let's say in this area, we do not have the access to measure the channel knowledge. And how can you make use of the incomplete measurement together with the data set to reconstruct the complete CKM? Similarly, if we only have the low resolution measurement, let's say if we can only measure channel knowledge for every 10 meters or 20 meters, so this corresponds to a low resolution CKM image, can you learn from the data set so that we can reconstruct a high quality or high resolution CKM? So this is a CKM super resolution problem. And the third case is that let's say if our measurement is noisy due to the imperfect devices, so can you learn from the data in the CKM data set so that we can remove the noise? So this is a very classical denoising problem. Okay, so all these problems requires us to have the high quality data set, let's say in the CKMImageNet. And actually about 4 weeks ago, we discussed how to use AI models for CKM construction. And we have framed the CKM construction problems as image processing problems or as an inverse problem. So Y is our partial observation for the CKM or for the environment, and X is our complete CKM where we need to reconstruct. But we only have the partial and even noisy observation. But as we mentioned just now, we can make use of the data set to learn from the reconstruction of X from Y. So we have the different techniques. Okay, so we discussed the different techniques in our previous lectures, and in this talk, we just emphasize that it is quite important for us to learn from the high quality data set, and we need to make use of the different techniques to construct a high quality data set for CKM AI-based construction and utilization. So this is just one example of the data set, but another scenario we need to consider is that is it possible that we can construct the data set very efficiently? So there are some limitations of the traditional data sets, like the CKMImageNet data set. It is unable to customize the CKM maps for the transceiver configurations because it is very troublesome to run the ray tracing software, let's say the Wireless Insight and Siona, because we need to have a very long time, to spend a long time for the data preparation or for the configuration. And is it possible that we can develop a platform so that we can generate the CKM data or channel knowledge data very efficiently? So this is the main motivation for this platform called the CKMImageGen. Gen means generation. So it generates the CKMs. We try to generate the CKMs for any locations in the world with very simple promote or with very simple configurations. It is very easy to customize our configuration, our transceiver configuration, our location configuration. It only requires, let's say, the image or text input and very user-friendly. And most importantly, this platform, we try to develop this platform as a multi-model autonomous data engine for CKM generation, and it is empowered by a large multi-model model. not just a large language model, LLM, but large multimodal model. So here is how it looks like. We try to generate CKM or channel knowledge map for certain input. Let's say this is the output. We try to generate channel knowledge map. Let's say the channel gain, channel angle map for certain environment. So this is the output we desire. The input is the environmental specification, as we mentioned previously, right? We need to specify some environment information. So this can be from the actual environment in the world. Let's say we need to specify the environment in Beijing or in Nanjing, and we need to give the location. One possibility is that we just give an image. We take a photo for that environment, and then this photo will actually specify the environment, because based on this photo we can localize most of the photo. If we have some landmarks of the environment, we can localize this the location where this photo was taken, so that we can retrieve the environmental information, let's say from certain maps, Google Map or Google Maps, so that we can have the environmental information for that location. So of course we can use the language models we can use some text or language to describe the environment. Let's say we try to generate a CKM for at 28 gigahertz, and the base station is located at some certain locations, and we set the building material to whatever. So we can specify the environmental information or configuration information based on the language. But how to interpret this language? Of course, we need to invoke the large language models. And how to process the image? We need to invoke the large visual models. So let's say we can use the Gemini or DeepSeek or whatever existing models. So in this case, we need to use the API for this kind of models. So in this case, we can extract the semantic meaning for the input, and we can reconstruct the environment, let's say either based on the location information, and we can have the environmental construction layer to extract the 3D physical map, or we can have a virtual environment, because let's say based on this language description, it is a virtual environment. It may not exist in the world, but as long as the reconstructed environment is consistent with the language description, that should be fine. So that basically means that we can have a reconstructed environment either corresponding to the realistic environment in the world, or it is a virtual environment. And we can specify the material, and we can specify the transmitter receiver locations. So with this, we can input all that information, let's say to the ray tracing software. Or let's say here is a Siona, because Siona is very user-friendly. We can use a Python to integrate all these modules into one single program. And then we get the CKM output. And this output, because it uses the ray tracing, so it will actually reflect the environment. And we do not need very complicated configurations. What we need is only this kind of environmental specification. So it is very efficient, and it can be made autonomous. And we can, as we mentioned just now, we can generate the CKM for the real world scenario or for certain virtual scenario. Okay, so in this case, we can generate the CKM anywhere in the world, just to input the image and the promote. So here we designed one graphic user interface for this platform. Here is the multi-modal configuration panel. You can input the image. As we mentioned, you can take a photo from the environment, and then you specify what you need. You want to generate this the CKM for this environment. You can specify what kind of frequency you want, and where you should put your base station location. And then we will reconstruct the environment here, and then the CKM will be constructed like this. So we can actually have this platform online, but due to the limited resources, maybe if too many people are using simultaneously, it may not be stable enough. And also for this kind of software, we need to use an API, so it actually will cost us some money to maintain this platform. You can have a try. So here is one demo. Here we take a photo and we input this photo to this panel, and then we will try to localize where this photo was taken. And then after located this photo, we try to reconstruct the environment based on the data from the Google Map or Baidu. And then we will do the ray tracing, and this is the corresponding CKM for this particular environment. Okay, so as we mentioned, this is just a very initial work. We try to make our data set generation very efficient and autonomous without having to do very complicated or sophisticated configuration. Okay, so this is all about the data set, and actually there are a lot of work to do. Before we mention the additional work or the future work we can do for the data set, we try to discuss very briefly the prototypes. So the first CKM prototype we try to introduce is based on the UWB localization system. We try to build a CKM prototype to support the beam alignment. So this is one of the useful applications for channel knowledge map. Here we have a transmitter, try to communicate with the receiver. Both the transmitter and the receiver have a large phase antenna array. So here we consider 28 gigahertz. And in the traditional system, without CKM, the transmitter and the receiver need to have the beam sweeping or beam alignment process. They need to try all the possible combinations of the transmit beam and the receiver beam. But with CKM, with channel knowledge map, we can localize the transmitter and the receiver locations, let's say based on the UWB positioning systems. So in this case, both the transmitter and the receiver need to carry a UWB tag. And this UWB system will localize the transmitter and the receiver, and we will build the channel knowledge map based on the locations, based on the historical data. Here we consider the scenario where this UE is moving in the environment, but in most of the scenario, we do not have the direct line-of-sight link between the base station and the UE. So we need to determine what should be the transmitter beam directions so that the signal will be directed towards the UE. And similarly, the receiver or the UE needs to determine its beam direction so that the signal will be received from the base station. So if without the CKM or without the environmental information, what we can do is that we simply beam the signal towards the UE or the base station direction. Of course, this will have very poor performance in this scenario because the direct link is blocked. So based on this measurement, we have this received signal power is very low. But with our CKM, the channel knowledge map, here in this case, we consider the grade, the different grades. We have the different preference for the beam index maps, so that we have the significantly improved performance, and the performance is even comparable to the exhaustive beam sweeping method. So this is how we use a prototype systems to demonstrate that a CKM or channel knowledge map is indeed quite useful for the beam alignment or for the communication scenario. And we even consider the dynamic environment. So here, the transmitter or the base station and the UE has already established the beam alignment in the millimeter wave environment. But let's say if we have the dynamic mobile vehicle that blocks this link. So in the traditional system, then after blockage, we need to re-establish the link. Let's say we need to restart the beam alignment process to try all the possible beams. But here, if we have the channel knowledge map, even before the vehicle blocks the link, we can do some proactive beam switching without waiting the link is blocked. And we do not need to do a beam sweeping because we have the channel knowledge map that will tell us which is the second best beam to say, let's say in this direction. So we find that we may have the so-called tuning free or beam sweeping free beam switching based on the CKM, even in the dynamic environment. So the details are given in this paper. And we even consider the UE scenario where the UE may change its orientation. So let's say the UE changes the orientation, whether it is still possible to use the CKM or the beam index map to enhance the wireless communication performance. Now we have shown that yes, it is possible as long as we have certain manner to make use of the UE orientation information and also, of course, the location information. Okay, so this is the prototype V1.0, and the limitation for this prototype is that it requires the external positioning systems. Here we use the UWB system to localize the mobile terminal locations, and the device needs to be cooperative and it needs to carry the positioning tags, and this system cannot sense the environmental information. So this is the limitation for the first prototype. And our solution for this is to use ISAC, or integrated sensing and communication. So the basic idea is like this. For CKM, we need the location information in order to query the channel knowledge map. And we also need the surrounding environmental information in order to construct the CKM. And actually, this kind of information can be easily obtained by ISAC, or integrated sensing and communication. So why not we use the information obtained from ISAC to support the construction of the CKM, and also to support the utilization of CKM, because the ISAC results can be used to construct the CKM and also to query the CKM. So this is how ISAC can benefit CKM. And in the reverse direction, if we already have the CKM or channel knowledge map, this information can be used to enhance the ISAC, or so-called environmental aware ISAC, because we have some prior knowledge about the environment. And we discussed 2 weeks ago how we can make use of the CKM to achieve even the non-nav site localization and sensing in the complex environment. So actually, for CKM and for ISAC, they have the mutual enhancement relationship. So we have the mutual enhancement between ISAC and CKM, and why not we make use of this enhancement to build our prototype. So in our second prototype, or prototype V2.0, we have developed an ISAC-based CKM. So the basic idea is like this. Let's say if we have a base station or a transmitter, and we have a UE, the base station will try to sense the environment and localize the UE. So here, the base station has a transmitter array and a receiver array, so it can be let's say a monostatic sensing. It can perform a monostatic sensing. So the base station may use the beams to sweep the environment so that we have the environmental information, and simultaneously it may also use the transmit signal to communicate with the UE, and the signal will be reflected by the environment and also by the UE, so that the received signal, the received antenna of the base station, may sense the environment and also localize the UE. So this is indeed the ISAC, simultaneous communication and the environmental sensing. So here is how our prototype looks like. the transmitter have the transmitter phase antenna array. We have implemented this prototype at a millimeter wave at 28 gigahertz, and the transmitter will send the signal, and the part of the signal will be reflected by the environment and also by the mobile terminal, and the other part of the signal will be received by the antennas of the communication UE to perform, let's say, the communication. And the reflection signal will be processed by the receiver antennas to perform the sensing signal processing to estimate the velocity, the distance, and the angle of arrival for the reflected signal. And the signal could be reflected from the environment. Also, it could be reflected from the UE itself. And this kind of information is very useful for CKM construction and the environmental sensing. So this is the basic setup. And here is how the result looks like. We have a mobile terminal moving in the environment. The environment could be complex and the line-of-sight link could be blocked. And we have the ISAC base station so that it can sense the environment. Let's say it can, here are the environment, the buildings, the walls, and here is the directions of the UE. So we can see that even the UE moves in the different direction, even in the non-line-of-sight scenario, this line will track the location, the directions of the UE. And on the left-hand side, we have the different colors as the UE moves. This basically means that as the UE moves, we have already collected the useful information about the wireless channel. Here it is the beam index. At this particular location, what are the best beams for this location? And this information is very useful, and it's used to construct the CKM. So this different color means that the UE has already traversed this location, so that next time, let's say here, next time a new UE or the same UE comes again, it can make use of the knowledge stored in the CKM, let's say to perform the beam forming without having to perform the channel estimation or beam sweeping again. So this is how we can make use of the ISAC to support both the CKM construction as well as the CKM utilization for communication. So the full video is available at this QR code. And but this kind of prototype is for some rather simple scenario where we have full control for the base station and the transmitter. We also try to really construct the CKM for the commercial base station. So in this case, we do not have the control to the base station. What we can do is that we can only passively measure the channel knowledge at the different locations with the base station. So here we developed a system so that we can have a cost-effective and real-time CKM construction solution with the commercial base station and for the 3D environment. So we can support the 3D CKM construction, line-of-sight state estimation, and the environment reconstruction. So here is our system. We have RTK antennas to precisely localize our UAV, not just based on the GPS localization. And we also developed a cloud server so that we can upload all the data by all the UAVs to the server so that we can store the uploaded channel knowledge data. And then in this case, we can further, based on the estimated data or the measurement data, to estimate the height of the each building or to reconstruct the environment. So this is still a very initial work, and hopefully we can make more progress towards this direction. And when talking about the ISAC with CKM, we also try to have an open source ISAC platform, because we try to make use of the, let's say, the CKM dataset to be open source. We try to make the CKM AI model to be open source. So for the ISAC, if we want to use the ISAC to support the CKM construction and the utilization, we try to make an open platform for integration sensor and communication as well. So here we have developed one platform, the fully open source and real-time OFDM ISAC platform, so that we can support the research and the prototyping. So here is a very simple scenario. Let's say we try to sense a target or a UAV. We have a monostatic base station, and of course, we can also support the bistatic base station. And simultaneously, we try to communicate with the receiver. Here, we do not need to use any FPGA development or any license for this kind of platform. And it can support both monostatic and bistatic sensing. And we have used some synchronization techniques so that we can have so-called wire-free bistatic sensing. And we can support a continuous wave OFDM design so that we do not have the sensing blind, just like in the past waveform sensing, we may have the blind issue, but here we have the continuous wave OFDM based sensing so that we can support the communication simultaneously. And it is compatible with a wide range of USRP hardwares. So actually this platform is available online. You may check my website, and also you may check my Bilibili video. There is some video introduction for this platform. So here is a basic scenario for this for this platform. For some reason the video does not work. So actually you may check the website, the Bilibili website for this detailed scenario. Actually we have implemented the character rejection and also the micro Doppler sensing capability in this open source platform. And you can make use of the source code in that platform. Okay. So due to time limitations, I think here are the main contents for today's talk. We first talk about the dataset, why we need a dedicated dataset for CKM, and we introduce one particular dataset. Of course, we also summarize, or we also overviewed the existing wireless channel dataset in the community, and we introduce one particular dataset called CKMImageNet. It is very useful because it can make use of any advanced computer vision techniques very efficiently, because all the data are organized in the image format. And we also developed one efficient system or platform so that we can autonomously generate the data for CKM. And also we introduced some very preliminary prototypes for CKM. The first one with UWB-based localization, the second one with ISAC enhanced CKM, and we try to open the source for the ISAC, open ISAC, so that we can have the real-time and open source OFDM ISAC platform. Okay, and of course there are many future works for this kind of data set and also prototyping. For let's say for data set, we need to consider different materials. We need to consider different models or multi-model environmental information. We will also need to consider both the synthetic data and also the measured data. So we have the heterogeneous data sources. We also need to consider the data in the dynamic environment. Okay, so here are some major references. We have the tutorial and the magazine paper, including the first paper that proposed the concept of the CKM in 2021. And in 2024, we have the tutorial paper for CKM. And we have the CKM dataset, some construction methods, and how to utilize the CKM, and also some prototypes, all are available in these papers. Okay, with that, I would like to conclude my talk, and you are welcome to ask any questions. Thank you.
Thank you, Professor Zeng. Professor Zeng just gave a detailed tutorial on datasets for CKM, including how to build datasets and how to utilize datasets. We have received many questions. The first question is about the slide mentioned that CKMImageNet is obtained via ray tracing using actual environment maps. However, in real physical world, material aging, weather changes, and dynamic obstacles like vehicles and pedestrians significantly affect the channel. When training models on CKMImageNet, how do we bridge this real to simulation to real gap to ensure the models remain highly robust in actual 6G networks?
Yeah, that's really a very practical and a very important question. It is related to the dynamic environment. Yes, indeed. So I think we can interpret this question from the following perspective. So for this kind of data set, we do not really try to directly use the data generated in the data set to do the actual channel knowledge prediction in our practical environment. What we want to what we want to use is the relationship between the environment and the actual data or the channel knowledge. So with ray tracing, we actually capture many of the features or many of the physical laws between the environment and the channel knowledge data. For example, the blockage, the reflection, the diffraction. So in this case, the data generated by this method is useful to learn the relationship or to learn the mapping from the environment to the channel knowledge map, CKM. But of course, as we mentioned, in practice, the environment is dynamic. So in that case, there are different possibilities. The first possibility is that, let's say we need to have additional sensing or additional method to capture the dynamic environment. Let's say just like we take the snapshots for the environment. For each snapshot, it is a static environment, but we can make different snapshots. And in that case, we can make use of the, let's say, any AI models to learn the relationship between the different snapshots of the environment and the CKM. But of course, I'm not sure whether there are already existing any work towards this direction. So because it is quite challenging, because if we want to do it like this. Another possibility is that, as we mentioned previously, maybe we can define our CKM as like a location conditional PDF so that it is more robust to the dynamic environment. But in the case, for the case of the dataset generation, I'm not sure how we can make use of the dynamic environment more efficiently. Another possibility, of course, is that you can generate many dynamic environments because now Wireless Insight and also Siona can support the dynamic environmental generation. And I believe that towards that direction, we can also make use of this kind of capability of the ray tracing software for the dynamic environment to generate more higher quality data set. But so far, we haven't tried that yet, but it will be a very useful direction to go further. Yeah, thanks.
Right, that makes sense. The second question, ImageNet revolutionized computer vision not just through its massive scale, but by establishing unified evaluation standards that ignited deep learning. Will CKMImageNet also release standardized benchmarks similar to image classification accuracy for different CKM construction algorithms, for example, interpolation versus generative AI? What unified metrics will we primarily use for fair comparisons on CKMImageNet in the future?
Yeah, that is really a very good proposal. Yeah, as you mentioned, yes, because of the CKM, because of the ImageNet in 2009, and also the computation by the ImageNet, the object recognition or classification by the ImageNet. So they have revolutionized the deep learning community. But I'm not sure. That is really a very good suggestion, and it is really possible. But I should say that I should be careful to make any overclaim for this kind of CKMImageNet data set. At this moment, maybe the quality is not good enough to support such kind of computation. But I believe that as a whole, if everybody, other groups can contribute to further enhance, first of all, the quality, secondly, also the quantity, the scale of the data set, it is indeed possible. For example, we need, let's say we need more diversified environmental information, and maybe we need more heterogeneous resources, as we mentioned just now. And then in that case, we may propose or we may initialize certain computation, just like the ImageNet computation. But as you mentioned, another issue we need to consider is that for ImageNet computation, it has a very clear objective, whether how accurate you can recognize the different objects. But here for CKM construction, we have many different tasks. It is not just the one single object recognition. Let's say we may have the CKM generation problems. We may have the impending super resolution. We may have the denoising problems. All these kind of problems could be the competition tasks for the different groups. We need to figure out which one should have the most benefit or most contributions to the community. That is not very clear yet. Of course, the simplest problem is how accurate your constructed CKM, let's say in terms of the MSE, as compared to the ground truth. But that is just only one aspect, and then many different aspects we need to consider in order to attract more people to contribute, and also in order to make meaningful computations to advance this research direction. But that is indeed really a very good suggestion. And if anybody or any group have this kind of willingness to cooperate, and I'm very happy to discuss further. Yeah, thanks.
That's right. There are still many practical issues that call for researchers to join this field. So the next question, CKMImageGen introduced large multimodal models, LLM, for end-to-end generation using only image or text inputs, which significantly lowers the barrier. However, generative AI often suffers from hallucinations. How does CKMImageNet ImageGen ensure that the generated channel data is not just visually plausible, but strictly adheres to physical electromagnetic wave propagation laws? Is there a hybrid validation constraint with ray tracing at the base level?
Yeah, that's a good question. Yeah, indeed, the large language models and also other models have the hallucination problem. But here I need to clarify that this existing LL models or LVM models is not used to generate the CKM. Let's say here we only use these models, let's say, to interpret the language. So let's say if we input the language description for the CKM we want to generate, then it tries to extract the useful information from this language, let's say 28 gigahertz, or what kind of CKM we want, based on this GEMNet. So it is not involved for the ray tracing or the channel knowledge data generation process. It is only used to interpret the language. So the generation process is here. In this sort of physical simulation layer, we actually use the ray tracing software, just like what we used in the CKMImageNet dataset. Here we use the Siona. The Siona is a open source software program developed by Invenda, and it has been widely used. So in that case, the quality, or whether there's a hallucination for the generated data, depends on whether there's an issue for Siona, because Siona is a ray tracing software. It does not have such an issue. And yeah, that is a basic scenario. But this process is this platform is basically trying to make the ray tracing more efficient and even autonomous. But the ray tracing, the data generation behind is the ray tracing. So it is not a generative AI-based method to generate the data. Yeah.
Right, that makes sense. The third question, how does the system's LLM brain actually infer building materials and spatial depth from just a 2D photo or text description to generate high-precision multipath characteristics?
Yeah, that's really also a good question. Yeah, I need to again clarify. Maybe I didn't make it quite clear. This image is not trying to give the environmental information of the actual environment. This image is used to localize, trying to find where this image was taken. So as we can see here, let's say if we take an image, this large language model or large visual model will be invoked to actually localize this location, and then it will let's say query the Google map to find the environmental information of that particular location. So the environmental information is from the Google map or from the Golden map, so that we have the 3D buildings, and then based on this building's environment, we reconstruct the we will use ray tracing software. So okay, it looks how it looks like, and the input, the image is input to this panel, to the platform, and the environmental information is like this. It is extracted from the existing 3D maps for the Google map. Yeah.
All right. The next question, the audience was wondering if we could write a script into Sionna to define how to handle the received signals and how then directly generate the data sets. And then this, the audience also asked the same question, how can the sim to real gap be resolved? Which I think you have already responded part of that.
Yeah, indeed, here we use a Python script to make use of the Sionna to generate the CKM. This is exactly what we are doing, and what we make this is that what we're trying to do is that to make this very efficient and autonomous, so that we need to specify a method we need to define a method to specify the environmental information, how to get to the environment, because for the ray tracing, we need to specify the environment in a certain way. Either it is a realistic environment in the world in certain locations, or it is a virtual environment. As long as we can specify the environment before the ray tracing software, and this is the Sionna, then we just need to make use of this software to generate the data. And then our next step is that whether it is possible or whether we should replace this Sionna, because Sionna, it also takes some time to process. So that's why this task is mainly used to generate the data, and the data can be further used to train an AI model or whatever model to facilitate the ray tracing software, the ray tracing process, or even to accept more multi-model inputs, not just the full wireless environment or physical environment. So that is the basic philosophy.
Yeah. The next question, regarding dynamic environments, introducing pedestrians and vehicles certainly makes the CKM more realistic. Does this imply that the future CKMs will require extremely high-frequency real-time updates, much like high-definition maps for autonomous driving?
Yeah, this is indeed a good question. My understanding is that no, we should not define our CKM like that. If we define our CKM like that, if we want to consider every aspect of the dynamic and static environment, then I don't think the CKM will be very useful. So our basic philosophy is that if our CKM is defined like this, it is still a stochastic knowledge. It is not a deterministic. Let's say if you give me the location information queue, I will give you a probability distribution of the channel knowledge, not a deterministic channel knowledge. So in that case, every dynamic aspect can be included in this distribution. So the key point is that this distribution is different from the traditional channel modeling distribution. In our traditional channel modeling, we also model the channel as a distribution. But here we have the location specific distribution. So it is unique. It is specific to this location, so that any environmental dynamics should be reflected in this distribution if we have learned this CKM, learned this environment for a long time, because the distribution we can treat it as is kind of static or stationary. So in this case, we can avoid the need to update the CKM or to learn the CKM in a very high frequency, let's say in the millisecond or even in the second. That is not feasible. Yeah, that is my understanding. But of course, there are many different tasks in order to achieve this this vision.
Okay, this is the last question. Is there any scenario where the accuracy of generating the channel map been refined?
Yeah, that is a good question. In our different papers, so I'm not sure how to interpret verified. Maybe the most convincing method is that we need to verify the result based on the measurement results, right? That is the case. Or even we need to verify the result based on our performance for the downstreaming tasks. But at this moment, we haven't done that yet. What we have done is that we have make use of whatever AI methods, or let's say let's say here the diffusion method to reconstruct or to generate the CKM, and then we use a very standard method to verify the performance in AI community. Let's say we split our data into the training data set and the verification data set, and then they are completely random and they are not overlapping. And then the training model does not see the verification data. And then after the training, we try to verify with the verification data set. So this has been done. And this basically shows the effectiveness of the model. But we haven't tried the verification of whatever reconstructed or generated data with the measurement data. Yeah, because we do not have enough measurement data, and that is really a tedious process. And another possibility is that we first use this existing data to train an AI model. Then we use a mixed the synthetic data or simulation data together with the measurement data to do the verification. But I think that will be a future work. Yeah, thanks.
Yeah, thank you so much, Professor Zeng, for answering many questions from our audience. In the interest of time, we may not have gone over all the questions, but Professor Zeng will give some feedback on the Jasper platform in case you have further questions. So here comes the end of this lecture, and hope that this lecture has further raised your interest and knowledge for CKM. Next Wednesday, same time, we will have our 10th lecture, which is the last lecture in this mini course series. And the next lecture will be delivered by Professor Ray Zhang from National University of Singapore on channel gain map estimation based on virtual scatter models and future directions. Let's thank Professor Zeng again, and see you next Wednesday, same time.
Thanks. Bye-bye.
Bye.